In this chapter, we will be looking at logarithms. In this lesson, we will be looking at logarithmic word problems. To begin, we will look at problems involving the Richter scale.
Okay, so when it comes to word problems and logarithms and the applications there's really only three that we look at closely at high school here. And then we're going to look at the Richter scale, okay? We're going to look at the pH scale, and we're going to work with decibels. And they're all basically doing the same thing. Each one's got their own little twist to it, but they're basically even the same formula that we're going to be using, with just a couple minor little tweaks as you go from one specific topic to the next. So now we're going to start with the Richter scale. Here, I'll zoom in a little bit here. So the Richter scale is used to measure earthquake intensities, right? Okay, and I think we all know that. We've heard about that every time there's an earthquake somewhere in the world. Then you hear the measure, the size of it on the Richter scale. Now, but it helps to understand how the Richter scale works here. It's a logarithmic scale, which means that every change in one value on the Richter scale causes a 10-fold increase in the intensity of the earthquake. Now, when we talk about intensity, we're talking about energy. Okay, in the energy released is maybe a better way to say that. Energy released. So, for example, if you look at our little chart over here, notice that we've got in 1966, we've got the 6.9 level earthquake in Turkey. The one in San Francisco in 1906 was 7.9. Okay, so because there's a one-step difference on the Richter scale between those two, that means there was 10 times more energy released in the San Francisco earthquake than there was in the Turkey earthquake. However, in 1933, there was an 8.9 level magnitude earthquake in Japan, and because that's two full steps above the Turkey earthquake here, this one is 100 times more energy coming off of this. So you have to understand the way this scale works to really get a sense of how we compare earthquakes, okay? So, and the example that they give over here is the one in Guatemala at 7.5 is 10 times as strong as the one in Italy at 6.5. So when we compare earthquakes, what we're going to do here is, now this should be intensity over intensity, okay? Like what we should be getting here is the ratio of intensities here. Is it going to equal to 10 to the magnitude of the top quake minus the magnitude of the bottom quake, okay? So you might think of this as intensity 1 divided by intensity 2 is equal to 10 to the m1 minus a magnitude 1 minus magnitude 2. Now these magnitudes here are the measures on the Richter scale. And again, intensities deal with the amount of energy released. Now the reason why the equation is kind of written like this is because in most cases you're going to be given the ratio of their intensities. You're not going to give you specific amounts of energy that you're going to compare. So this is the equation that we're going to work with, and this is one I really strongly suggest that you memorize. Often on exams, major exams like the diploma, you're given other forms of this equation, but eventually you got to work it down to this one to answer the specific question that they're asking. So now we'll take a look at some questions here.
How many times more intense is an earthquake of magnitude 9.5 than one of 7.8?
Okay, so this first question is asking us to compare the intensities of these two quakes here. So we get I1 divided by I2 is going to equal 10 to the magnitude of the first quake minus the magnitude of the second quake. So what we're looking for is this ratio here, and we're going to get it by plugging this material in. So in this case here, that ratio of intensities is going to equal 10. Well, okay, the larger earthquake that we've got here is 9.5, and the smaller earthquake is 7.8. So we're going to figure out how many times more intense this one was than this one. So this will be 10, and you just go to your calculator here and plug this in. 10 raised to the power 9.5 minus 7.8, and you're going to get something that's approximately equal to 50.1. Okay, so in other words, it was 50 times larger, or 50 times more intense. Okay, more intense. 50 times more energy was released in the 9.5 earthquake than in the 7.8 earthquake.
How many times more intense is the 2011 earthquake in Japan with a magnitude of 9.0 than the 2012 Peru earthquake of magnitude 6.3?
Here's another question where we're being asked to compare the intensities. And then remember, the intensity of the first quake compared to the intensity of the second quake will equal 10 to the magnitude of the first minus the magnitude of the second. So now, to compare these specific intensities, we're going to use their magnitudes off the Richter scale, and what we've got here is 9.0 and 6.3. So this will be to the 9.0 minus 6.3. Now notice here that this difference here is more than 2 but not quite 3. So I suspect that this is going to be somewhere between 100 and 1,000 times bigger. No, certainly no more than that, and no less than 100. So somewhere in that range right there. That's just me kind of taking a stab at that there. And it turns out when you plug that into your calculator, you will get approximately 501.2 times greater. So in other words, this thing is roughly 501 times more intense. Okay? So in this case, not only was it between 100 and 1,000, it's kind of close to the middle of that. So anyway, there you go.
A major earthquake has a magnitude of 6.5, and it is 723 times as intense as a minor earthquake. Find the magnitude of the minor earthquake.
All right, now this question is asking for something a little different here. In this case, we know what the comparison of the intensities is. Okay, so we're still using this equation right here. But in this particular case, we know that the first quake is 723 times as large. So that ratio there is going to be 723. And this is going to equal 10 to the, now the magnitudes here. Now a major earthquake has a magnitude of 6.5 and is 723 times as intense. So the 6.5 is coming from the larger quake, so that one comes first. Okay, so minus the magnitude of the second quake there. Now, how do I solve this here? What do I do here? Well, you know what? What we're going to do here is we're going to convert this into a logarithm. Okay, we're going to convert this into specifically into a common log. Okay, so we're going to get here the log. Okay, now think about this. The base is this 10, so the base here is going to be 10, and I don't have to write it if it is. That will equal 6.5 minus m2, magnitude of the second quake. And then whatever's on the other side of that power, that's what goes inside the logarithm. Now, I just have to manipulate this equation here to solve for m2. Okay, so what I would do is I would bring the m2 over and bring the log of 723 over. So the magnitude of the second quake will equal 6.5 minus the log of 723. So again, just to reiterate what we're doing here, we've got this exponential function here. My unknown is in the exponent. What I'm trying to do here is get that out. So I convert this to the logarithm. Okay, that's what you do here when you're solving an exponential equation. You use logarithms. Okay, solve for the unknown. And now this is just calculator work. So now let me do this with you here. So 6.5 minus the log of 723. Whoops, 723. So 3.64. Okay, so 3.6. So the magnitude of that second quake here is roughly, approximately 3.6 on the Richter scale.
A major earthquake of magnitude 8.2 is 110 times as intense as a minor earthquake. What is the magnitude of the minor earthquake?
Okay, and this question here is very similar to the one that we just did. So again, we've got the comparison of the two intensities here. And we know, in this case here, again, we know this comparison. We know that the larger quake is 110 times as intense. So the ratio I1 to I2 is 110. The larger quake is 8.2 on the Richter scale. And what we're looking for is the magnitude of that second quake there. And like we did before here, what we're going to do here, because this is set up beautifully for it, we're going to convert this to the log form. Okay, we're going to, this is a base 10 here, so we're going to use the common log. So this will be log base 10 of, now it turns out this is going to be 110, and then remember the logarithm is equal to the exponent, so 8.2 minus m2. It doesn't matter that there's a binomial in the exponent, the logarithm is equal to the exponent. So now I'll bring the magnitude over, bring the log 110 over. So that magnitude of the second quake will be 8.2 minus the log, whoops, of 110. And we'll just go to the calculator. Okay, and we got 8.2, there we go, minus the log of 110. And there we go, 6.2. So this is going to be approximately equal to 6.2 on the Richter scale. And there you go. Now you've really only got these two types of problems that you're going to get asked with earthquakes, and actually with decibels or pH, it's basically going to be the same thing. you're either going to be asked to find the ratio of the intensities, or you're going to be asked to find a magnitude, a measure on one of those scales.
Now we will consider problems involving the decibel scale.
Okay, so now we're going to take a look at the decibel scale. Now, the decibel scale is a little different than the Richter scale. There is a more direct comparison here, and we'll talk about it right here. We'll say it like this: sound is measured in decibels, but the scale works like a Richter scale if the sound is in bells. Now, okay, so there's two different measurement units here. There's bells and then there's decibels, okay? Essentially, the decibel scale is what you might call a little bit of a finer scale here. There's 10 decibels per bell. Bells are exactly like the Richter scale, okay? So, for example, if you had, we're going to now compare the intensities of two sounds. The intensity of the first one over the intensity of the second one would be 10 to the bells of the first one minus the bells of the second one, okay? It's exactly the same formula. Decibels are a little different because decibels, like I said, are a little bit of a finer division. There are 10 decibels in every bell. So now, but that's the more commonly used measure for comparing sound intensities here. So now we're going to take a quick look at the decibel scale here. So here's a kind of a list of some sounds here and approximately where their decibel levels are. Because of the way the scale works here, because we're in decibels here, and we're now multiplied these bells by 10, the division's a little bit finer here. The jump is similar to what we did with the Richter scale, but here we got to consider that everything's been multiplied by 10. So whereas on the Richter scale, when you went up 1 unit, and that corresponded to a multiple of 10, here when you go up 10 units, that's a multiple of 10. So to go from, for example, a measure of 40 to a measure of 50 in decibels, that sound here at 50 is 10 times louder than the one at 40. If you go from 40 to, let's say, 60, because that's 20 decibels larger, that corresponds to a multiple of 100. If you were to go from 50 up here to 100, that little jump right here, okay, because that's 50 decibels louder, that's going to be 10 to the 5 or 100,000 times louder, okay, the sound at 100 decibels compared to the sound at 50 decibels, okay. So just so that you have an idea of the way the scale works here. Again, very similar to the Richter scale, but because of that multiple of 10 in there, you just have to realize, that that's there, okay? So now we're going to take a quick look at another equation here. So to determine the level, sound level in decibels, and this should actually say decibels here. We're going to use B, and actually it probably makes a little bit more sense to use dB here, but anyway, is going to equal 10 times the log of the intensity of the sound, or the amount of energy produced, plus 12. Okay, so when we do that first, and we multiply by 10, and that little 10 there's your conversion factor between bells and decibels. So if you wanted the bell measure here, this would just be the log of the intensity of the sound plus 12. Okay, so and you see that here. It says where B is the sound level in decibels, okay, that's the units here, and I is the intensity in watts per square meter. Now just think about the way that's being measured here. So you got your sound source here, and then basically when you got something producing a sound, it produces this kind of pressure wave that opens up like a sphere around that object there. And so what we're measuring really is the amount of energy per square meter of that sphere that expands away from that sound, and that's how we're measuring the energy. Anyway, so now we're going to take a look at a couple of questions related to this.
A power saw at 120 decibels is how many times as loud as a telephone dial at 80 decibels?
All right, so in this first question here, we're comparing two sounds. So we want to know how many times as intense is the one than the other here. So we're going to use this formula right here, I1 over I2, and this is going to equal 10 to the decibels of the first minus the decibels of the second over 10. We're going to throw that conversion factor in here. So now in this case, the comparison of the intensities here is going to be 10 raised to the power saw is at 120 decibels, and the telephone is at 80 decibels over 10. Actually, this isn't all that hard to do because 120 minus 80 is going to be 40. Divided by 10 is 4. So this is 10 to the 4. So this is going to be equal to, 10 to the 4 does not necessarily start with a 4. I was going to make that, I was going to put the right number of zeros there, but I was going to put a 4 there. Okay. So there we go. So the one sound here is going to be 10,000 times louder than the other one. The power saw is 10,000 times louder than the telephone.
What is the sound level in bells of an ordinary conversation if the intensity of the sound is 3 times 10 to the negative 6 watts per meter squared?
So in this case here, we're going to ask what is the sound level in bells of ordinary conversation if we know the energy being produced here. If energy is 3.0 essentially times 10 to the negative 6 watts per meter squared. So we're going to use our equation here. Now remember, this is going to be the magnitude here, the sound level. It's going to be 10 times the log of I plus 12. Now this is going to give us the answer in decibels. And that's okay. What we'll do here is we'll convert that to bells in just a couple seconds here. But I'm going to enter this in, and this will be 10 times the log of 3 times 10 to the negative 6 plus 12. There are a couple of different ways that I can do that. I'll show you my calculator here. So if I enter 10 and then bracket the log of, now I can do this as 3 times 10 to the exponent negative 6. First of all, then close the logarithm, add 12, and then close the brackets for the multiple of 10 here. And I'm going to get 64.8 decibels, okay? So 64.8 decibels. Now I could have done that a different way, and I'll show you here. I could have multiplied 10 by the log of, and I'll enter 3, and then I'm going to use this little bit right here, this EE. So I'll press second, comma, and what that does is that puts a little E right there. Now this is going to be engineering notation, scientific notation here. It's going to refer to 10 to the power of, and I'll just put negative 6 right afterwards. The calculator will recognize that little bit there means times 10 to the negative 6, and if I press enter, you'll notice you get the exact same value. So here's my answer in decibels. If I want it in bells, I would just take that answer and divide by 10 and get 6.48 bells. And that's what they're looking for.
And finally, we will look at questions that involve the pH scale.
So now we're going to take a quick look at the pH scale, because that's also a logarithmic scale. But there's a couple of things going on here that make the pH scale maybe a little bit more confusing to work with, but I'm going to try to my best here to simplify this as much as possible here. But first of all, notice this, that every time, okay, so that when we're talking about pH here, we're really talking about a measure of the hydrogen ion concentration in a solution. The more hydrogen ion, the higher the hydrogen ion concentration, the more acidic the solution, and the lower it is, the more alkaline the solution. Okay, so, and the way the scale works here is every time you take a step of 1, every time you take a step of 1 to the left here on the scale towards the smaller numbers, basically the concentration goes up by a factor of 10. Okay, so we're getting more acidic here, but the concentration goes up. So from 7 to 6, okay, there is 10 times more hydrogen ions in that solution. Well, moles per liter is the way we're describing it. Okay, there's 10 times more moles per liter for this fluid than there is for this fluid. There's 100 times if I compare 5 to 7. Okay, but it depends on which way you go and what the question is that you're asking. So we're gonna try to make that as straightforward as possible here. There is a beautiful little formula for calculating the pH using just the hydrogen ion concentration, and that is the pH of the solution is going to equal the negative log, common log, notice, of H positive, where that's the hydrogen ion concentration. Now, I'm going to do something here to kind of try to help this make sense here. We're going to solve for H, okay? Now, I would move the negative over, make this the negative pH is equal to the log of the hydrogen ion concentration. And now I'm going to convert that log expression, okay, to an exponential. Now it's common log, so the base is 10, which means 10 to the negative pH of that solution is going to equal the hydrogen ion concentration. Whoops, sorry, you can't see that. So here we go. 10 to the negative value of the pH is going to be the hydrogen ion concentration. Okay, good. Now, let's say that we're going to compare a couple of these. Okay, So let's say I know the hydrogen ion concentrations of two solutions. I'm going to compare them. So let's say that this up here, this is the hydrogen ion concentration of my first solution. This is my hydrogen ion concentration of my second solution. That fraction is going to be 10 to the negative pH of the first solution over 10 to the negative pH of the second solution. Now, let's assume right now that the approach is going to be that if this is the higher value, this is the larger value, so I'm going to be comparing, the ratio I'm going to be comparing here is how much bigger this is compared to this one. Think about what that means. If I'm expecting this to be bigger than this, and usually I am. Usually I'm looking for this to be some sort of nice big number, not a decimal number, a nice big number. So this is going to be larger than this one. This is comparing acidity then. Okay, this little expression here is comparing acidity because the larger the hydrogen ion concentration, the more acidic it is. And I want this to be bigger. But look what that does to this formula right here. Notice that what I'm going to do here is I'm going to subtract. When I try to combine these, because the bases are the same, I'm going to subtract the exponents. I'm going to find the difference in them. So this will be negative pH of 1, 10 to the negative pH of the first one, minus the negative pH of the second. I'm going to add the pH of the second one. Sorry, you can't quite see that. So look at what we've got here. And that, I can rewrite that in a slightly different order and make this the pH of the second solution minus the pH of the first solution. Now, I'm going to rewrite that a little bit lower here, but just to give you a sense of, you'll notice that I'm comparing the intensities, the concentrations of the hydrogen ion concentration, or sorry, of the hydrogen ion here. And that is a comparison of the pH. Now this looks very, very similar to the Richter scale, except that these two are reversed. And that's what makes this one unique. So now I'm going to summarize that down here. If I'm going to compare acidity, it'll be the hydrogen ion concentration of the first one. Whoops, sorry. Probably want that plus sign inside. Over the hydrogen ion concentration of the second one. I'm assuming that this is bigger because I'm comparing acidity here and I'm going to force the larger value up top here. This is going to be equal to the pH of the second solution minus the pH of the first solution. That compares acidity. If I want to therefore compare alkalinity, all I will do is I will use this formula, but then I'll reciprocate it at the end. Okay, so to compare, and I was going to say to find alkalinity, but that's not what I mean. To compare alkalinity, okay, reciprocate. Okay, now we'll take a look at a couple equations here where we do that.
How much more alkaline is seawater with a pH of 8.4 than pure water with a pH of 7?
Okay, so here we go. And here's a perfect example of what I was just talking about here. How much more alkaline is seawater at a pH of 8.4 than pure water at a pH of 7? Okay, so what I'm going to do here right now, I'm comparing seawater to pure water. I'm comparing seawater to pure water. So this is going to be the hydrogen ion concentration of seawater. And we're going to compare that to the hydrogen ion concentration of pure water, because this is the comparison that I'm being given. Now, this will be equal to the 10 to the pH of pure water minus the pH of seawater. But remember, this is going to compare acidity. That's what this equation compares. So this is going to be 10 to the pH of pure water, 7 minus 8.4. I'm going to go to my calculator here, and I'm going to get, 10, the exponent of 7 minus 8.4. And I get this ratio right here. So this is approximately 0.04. But this is times as acidic, which makes perfect sense because seawater isn't really more acidic. So it's not going to be, it's some fractional value if you're comparing acidity. Now, to get alkalinity, if you're going to compare alkalinity, reciprocate. So I'm now going to go to my calculator, and I will use this button right here. So I'm going to just press that right now. That'll take that number that I just figured out and flip it. So therefore this is approximately 25.1 times more alkaline. That's the comparison that we're looking for. The formula that I came up, or that we developed here just a couple minutes ago, is designed to compare acidity. We're comparing, whenever you're comparing one to another, okay, you're comparing seawater to pure water here, okay? So we put seawater in the numerator, pure water in the denominator. Sorry, I stumbled over my words here. That's what I'm trying to say here. When I'm comparing this one to this one, I am comparing acidity. If I want alkalinity, I reciprocate it at the end.
Determine the pH of a solution with a hydrogen concentration of 3.4 times 10 to the negative 4 moles per liter.
Okay, this question here is actually substantially easier than the one that we just did. Just determine the pH of a solution, and they give you the hydrogen ion concentration right here. So my pH is simply the log of that hydrogen ion concentration. Sorry, the negative log of that hydrogen ion concentration. So this will be the negative log of 3.4 times 10 to the negative 4. Now I will go to my calculator here. Negative log of 3.4, and I'm going to use that engineering notation. I'm pressing second comma right there. Okay, and what was it? Negative 4, so negative 4. When I press enter, I'm getting, and I'll round that, roughly 3.5. So this is approximately 3.5. That's my pH. Okay, there you go. It's as simple as that when you're looking for pH.
What is the hydrogen ion concentration of a tomato which has a pH of 4.21?
So in this question we're doing the reverse of what we were doing in the previous question. This time we're looking for the hydrogen ion concentration. So we've got the pH. That's negative log, okay, of the hydrogen ion concentration. I'm looking for the hydrogen ion concentration right now, so I'm going to move the negative over, so negative pH. And then I'm going to convert this to exponential form. It's a common log, so the base here is going to be 10. So this will become 10 to the negative pH is equal to the hydrogen ion concentration. Now in this case, the number that we're given for the pH is 4.21. So this will be 10 to the negative 4.21 is equal to the hydrogen ion concentration. Now that's great. There's nothing wrong with that number. That's a fine answer, but you're never going to answer it like that. Okay, that would not be the way you'd answer it. You want to write that in scientific notation. So what you got to do here is we're going to take our calculators and raise that 10 to the power of negative 4.21. That's the number that we want here. So approximately 6.17. So the hydrogen ion concentration here is going to be approximately 6.17 times 10. I just got to take a quick look there, to the negative 5. And this will be moles per liter. And that's what I got to do. I really can't leave it like this. I need to put that in the proper form for expressing that quantity. So there you go.